And we're back. Welcome back from the weekend and happy Tuesday. Today we'll switch gears and start material in Chapter 5, namely on scheduling. And scheduling is all the considerations or concerns all the considerations that one needs when you're trying to maximize your CPU utilization. But before we begin, let's get to some administrative bits. The reading has updated by the 29th of this month. Please make sure you are reading chapter sections 5.1 through 5.5. That's pages 199 to 227 in the main text. And so the objective of this module is to introduce the idea of CPU scheduling, which is the basis for multi-programming, the ability for your operating system to give you the illusion that it's doing more than one thing at the same time. We'll also describe a number of CPU scheduling algorithms. We'll discuss evaluation criteria for scheduling a CPU scheduling algorithm for particular systems, and we'll also examine scheduling algorithms for several operating systems. Okay, so basic concept, the idea behind multi-programming was to maximize the amount of time for which a CPU, central processing unit, is utilized. And so this is accomplished by effectively sharing the time on your CPU fractionally with a number of programs or tasks or processes, more correctly, that need to accomplish something. And so you have two different types of processes. There's something called an I/O bound process, and there's a CPU bound process. And we talked about that in a previous module. And now we're going to introduce a little bit more terminology, something called a burst cycle. Now, a burst cycle represents the execution of your process on the CPU for some period of time. And so you have these CPU and I/O burst cycles as your process executes, whether it's CPU bound or I/O bound. And from the perspective of your CPU, you're going to have a cycle of execution of different types of processes on the CPU. So it'll execute something that's CPU bound, and then you'll have an I/O bound process run, and then CPU bound, and I/O bound. Now, when you interleave in time these CPU bursts with these I/O bursts, effectively you get better utilization of your processor. Now, certainly if you're going to perform an I/O burst, some of that time is spent waiting for I/O. And so these I/O bursts tend to be a lot shorter, if you will, time-wise, as far as their execution is concerned on the CPU. And so the CPU burst distribution, that proportion of process executions on the CPU over time, the distribution between the CPU burst and the I/O burst, the representation of the fractional use of the processor's time, is the main concern when it comes to increasing or maximizing CPU utilization. And so if we look at CPU burst times, a histogram of them, here we have on the horizontal axis, we have the duration of that burst. So that's the amount of time in milliseconds that a process spends executing on a CPU. And then on the vertical axis, we have frequency, the number of processes or number of bursts, and that's a vertical axis. And that's just the counts, just a number, no units on the vertical axis. So what you see here, if we look at this peak, the largest number, it's about 150, 152 of our bursts are in this very small duration, around 3 milliseconds. And so the burst times tend to be relatively small. And certainly we said we're interleaving CPU-bound processes with I/O-bound processes, and I/O-bound processes, because they have to wait for I/O, they're going to be relatively small in the burst time. And you see that reflected here with a very small 3 millisecond burst time as being the most numerous amount of times that a burst proceeds. It's about 3 milliseconds, which is relatively small. You do have some longer bursts here. So you have about 5 16 millisecond duration bursts. You have about 5 8 millisecond duration bursts. When we go to 4 millisecond, it's about 30 of them. But for the most part, 3 is dominating, 3 millisecond burst time is dominating the counts of all the bursts that are measured for a particular CPU. And so the short-term site scheduler, we said before, selects from among the processes in the ready queue, and it allocates the CPU to one of these processes. And we said that it takes the process structure, the process task structure in Linux, and it takes that information from those data structures for that particular process, and it loads them onto the CPU. Vice versa, when we're changing processes, the CPU's state for that process is copied from the CPU and sent into that particular process's data structure, the task structure in Linux. And so the scheduler, short term, takes processes in the ready queue and allocates one of them to the CPU. Now, of course, this queue, we know that a queue data structure is first in, first out access semantics, but it can be ordered in a number of different ways, and the ways in which it's ordered can impact our CPU utilization, and that's why we study scheduling as its own module in operating systems. And so there are a number of scheduling decisions. The scheduling decision is the selection of a process from the ready queue for allocation on the CPU. And so a scheduling decision can take place in a number of cases, and there are 4 of them, when you switch from running to waiting. So that means that you're going to be kicked off, you being a process, off the CPU, and you're going to join the wait queue, perhaps for some device. 2, when you switch from running to ready state, so that means your unit of time for execution on the CPU has ended, and now you have to go back into the ready queue so that some other process can be selected for execution for some period of time on the CPU. The next one, 3, is switching from waiting to ready. So that means you are on a wait queue, you being a process, waiting for I/O to complete, or some device to complete its I/O. And that device is ready, you get the data, and now you go to the ready queue. You're no longer on the wait queue for the device. Your interaction with that I/O device is done. And so a scheduling decision is made then. And then also when a process terminates, a scheduling decision is made. And so under that first case and the fourth case, namely switching from running to waiting and termination, that's non-preemptive. And what that means is that the process itself does something that causes a scheduling decision to occur. Now, the opposite of non-preemptive is preemptive. That means that the process that was executing on the CPU was halted, right? It was cut short. Well, not really cut short. It was halted, and that's called preemptive. So non-preemptive means that you are done with your execution, your burst, be that I/O burst or CPU burst. Preemptive means that you weren't done necessarily, but you were stopped by some external force or factor. Okay, and so all other scheduling, cases 2 and 3, those different points, those are preemptive. And if you think about some process being halted from its execution, you have to consider all sorts of resources that that process might have collected or might be interacting with. So think about shared data, right? If you're looking at shared memory, you have to think about what's going to happen if you're preempted. What about if you're in kernel mode? So let's say you execute a system call and you trap, and now the mode bit is set to kernel mode, and the kernel's executing something on your behalf. What happens when you're preempted? Or also interrupts. Suppose you have an interrupt that's firing for some critical operation, perhaps for interacting with an I/O device or doing some OS activity. What do you do if the process is being preempted? And so let's take a look a little bit at context switches. We have the vmstat system program, and if you give it this -s, it's going to tell you all the context switches that have happened. And if you look at the special file system called the process file system, there are various device files and special files in Linux that allow you to view all sorts of aspects of the machine. You can look at the status of a process using this special file system, which when you open it or read it, you're going to be able to get status information for various processes. So let's bring up VirtualBox, and we'll actually take a look at these and come back to the slide deck. All right, so I will see you in Ubuntu Linux. So we are in Ubuntu Linux, and we're going to try out some of these commands, vmstat and the proc file system. So let's do a manual page, vmstat, to take a look at the instructions. So vmstat reports virtual memory statistics. And if we look at the options on the command line, -s says, give me a table of various event counters and memory statistics. So if I write vmstat -s, well, it gives me the total number of kilobytes of memory, the amount of free memory, amount of inactive memory, and if we say pages swapped in, pages are a unit of chunks of memory that are brought in from disk into your main memory. And if we look swap CPU ticks, idle CPU ticks, pages, interrupts, and this number here, CPU context switches. And so we have, at the moment, we have 29,905,992 CPU context switches. So that means over 29 million times the scheduler has selected a process for execution on the CPU. Now let's look at the proc file system. So let me look at the ls/proc, and inside of proc I have process IDs. And so if I look at PS, I have process IDs. One of them is for the shell that I'm running. It's process ID 2269. And so if we look inside of this proc file system, I'll have a 2269 directory, and that's for process ID 2269, which is for this command line interface that I'm running. So if I do an ls list proc 2269, you'll notice one of the things I have something called the stat file. So if I do an ls on the stat file, instead of this ls, let's do a cat. So we're going to list out what's on this stat file. It'll give us the statistics of the process running the command line shell that you see here. So here, the stat, it has a certain meaning. Let's look at stat, and we can look that up another time. But all of this is status information that's meaningful, and it's formatted. If you Google search, you'll find information about the format of the stat file. And you can use this programmatically to read and get the updated status for every process that's running on the system. Okay, so let's switch back to the slides. I will meet you in PowerPoint. So we're back in PowerPoint, and we just demonstrated the number of context switches using vmstat-s, and we also showed the status file for the process ID for the command line interpreter that we're running in Linux. All right, so let's take a look at this dispatcher. How exactly does this context switch happen? Now, the dispatcher is that module that actually physically switches or does the work of switching between different processes as far as putting their information onto the CPU and getting information from the CPU into the data structure for that process. And so whenever the short-term scheduler makes a selection for the next process execute, it's the dispatcher that physically performs this giving of control from one process to the next process. And so this involves switching context, switching to user mode, and then jumping to the proper location in the user program in order to restart that program. So it could be the program initially runs, starts in the main entry point, main routine, or it could be resuming where it left off. It's loading the program counter of the CPU. And so it takes time to do all this copying back and forth, and that introduces latency, so-called dispatch latency. And this is the time it takes for the dispatcher to stop one process and to start another. So let's look at this figure, and this is in the book. And here we start out with some process P0 that's executing. And let's say, for the sake of consideration, the short-term scheduler selected process P1 to execute next. So what happens then? So process P0 is no longer executing. Its state is saved into the process control block, that task structure that saves all the data structure information associated with process P0. And it's populated by taking information from the CPU, all the information we talked about, like the register file, the stack pointer, the program counter, the data section, and so forth, and the text section. All of that state is saved into the process control block, that data structure or task struct for process P0. So then, when the dispatcher knows that process P1 is going to be the next one to execute on the CPU, it looks up that process control block for process 1, and it reads all that information out of that data structure, and it populates the CPU, like the program counter, the register file, and so forth, with that state that was stored in the process control block for process P1. And then process P1 is set to executing, and it runs on the CPU. And so all of that saving state of the old process, restoring state for the new process, and then starting the execution, that is performed by the dispatcher, and the time it takes to do these things is called the dispatch latency. So let's take a look at scheduling criteria. So the scheduling criteria, as we said at the outset, is purpose with maximizing your CPU utilization. And that means keeping it as busy as possible, because you don't want to waste this precious resource. The CPU is probably the most expensive part of your entire system. Moreover, why have all of this hardware if you're not going to make use of it efficiently? And so this idea of throughput talks about the number of processes that complete their execution per unit time. And so not only do you want to keep the CPU busy, but you want it to do a lot of things and make a lot of progress for each unit time on the CPU. And so this other thing called turnaround time is the amount of time it takes to execute a particular process. So you want processes, you might have 5 of them, 10 of them that need to share the CPU. You want them all to have a small turnaround time. You want them to complete running or perform what they're doing in the smallest time possible. Then there's also this other criteria called the waiting time. That's the amount of time a process is waiting in the ready queue. And so if you are not executing on the CPU, you're waiting, and that adds to the amount of time it takes for that process to execute. And then you have response time. Now, response time is a little bit different. It's the amount of time it takes from when a request was submitted until the first response is produced. Now, of course, first response is produced doesn't necessarily mean output, but it's making progress. So this response time, responsiveness, can be an important thing as far as users of a system are concerned. It gives them the illusion that something is happening. All right. And so in a scheduling algorithm, the idea that you want to optimize, there are lots of different criteria that you can employ. You might want to maximize CPU utilization, keep it as busy as possible. Maybe you want to maximize throughput. You want things to happen as quickly as possible. Maybe minimize the turnaround time. The time it takes to get stuff done is as small as possible. Minimize the waiting time. You don't want things to wait too long, or maybe minimize the response time for it to appear as responsive as possible. So when you have a scheduling algorithm, this algorithm maintains some objective, some primary thing it's trying to maximize or minimize. And these various criteria that I mentioned are all things that a scheduling algorithm might want to key in on as maximizing or minimizing. So let's look at some of these algorithms. We'll start with simple one, first come, first serve, or FCFS. Now, with this first come, first serve, as the name would imply, the process that arrives first to the ready queue is the one that is scheduled for execution on the CPU. And so this looks just like a queue data structure. You add things at the tail, and then you remove them at the head. So if you arrive first in time to the ready queue, you as a process, that means you're going to be scheduled first, because in this case, with first come, first serve, the scheduler takes processes off the ready queue in the order in which they arrive, which is exactly what a queue data structure, how it operates. So let's suppose here, and I'll describe this chart, and this is also in the book. We have two columns. In the first column, we have the process, and let's say you have process 1, process 2, and process P3. And then the burst time is the amount of time they need to run. So process P1 takes 24 milliseconds to run, process P2 takes 3 milliseconds, and process P3 lastly takes 3 milliseconds. Now suppose that the processes arrive on the ready queue in a particular order, and they arrive in order P1 followed by P2 followed by P3. So in that particular case, here's your queue, and here's the tail, and here's the head, and process P1 arrives, and then behind it is process P2, and then behind that is process P3. So when the scheduler takes items off the ready queue, it takes first P1 and then schedules it for execution on the CPU, and then it selects P2, and then it selects P3. And so we're going to represent the running of each of these processes for their burst time using a Gantt chart. And a Gantt chart is just a temporal chart that represents some action occurring for a period of time. So here, because P1 arrived first, we start at time 0. P1 is executing, and it runs for its full 24 milliseconds, and then P1 is finished. It exits. So then P2 is behind P1 in ready queue. So P2, which arrives second, it is scheduled for execution, and P2 runs for a total of 3 milliseconds. It starts at 24 milliseconds because P2 does not run until P1 is completed. So 24 is where milliseconds is where P2 starts. It has a burst time of 3 milliseconds, and so after that burst time has completed, P2 is now finished at time 27 milliseconds because 24 plus 3 is 27. So then the scheduler, the short-term scheduler, takes P3 off the ready queue. It has arrived third. So then P3, it does not execute until both P1 and P2 have executed. So P3 starts at 27 milliseconds. Its burst time is 3 milliseconds. And so P3 starts 27 plus 3 milliseconds, so it ends at 30 milliseconds. Okay, so this Gantt chart lays out in time what the execution is for each one of these processes, P1, P2, P3, using this first come, first served scheduling. And so if we were to look at the waiting time, we're going to add up the amount of time each one of these processes, P1, P2, and P3, waits. So we start out, P1 does not wait because it starts at time 0. So its waiting time is going to be 0. Okay. P2, it waits until P1 is done. So it waits a whole 24 milliseconds before it finishes, before it starts rather. So its wait time is 24 milliseconds. And then lastly, P3, its wait time is 27 milliseconds because it waits the first 24 for P1 and then another 3 for P2, and it starts at 27, so its wait time is going to be 27. So now we can calculate the average wait time. So we add up the 0 for P1's wait time, the 24 for P2's wait time, and the 27 for P3's wait time. We add them up, divide by 3, and we get 17 milliseconds as the average wait time. So we're going to compare this wait time to other approaches, and you can see that different scheduling algorithms will optimize on different criteria associated with process scheduling. Okay, so for first come, first served scheduling, suppose that these processes arrive in a different order. Now, if P2 comes first, and then P3 comes second, and P1 comes third, well, we order them differently. They're the same processes. We lay out the Gantt chart, and we're using the same burst time as before. So P2 has a burst time of 3, P3 has a burst time of 3 milliseconds, and P1 has a burst time of 24 milliseconds. And so here in this order, it's the same 3 processes, only we're executing them for a different ordering or a different arrival. It's still the same first come, first serve scheduling. So we lay out the Gantt chart. All right, P2, it starts at time T0 if it got there first to the ready queue. and it runs for 3 milliseconds. And then P3 starts after P2 is done because it's second in the ready queue for this new ordering. So it runs for 3 milliseconds, so it ends at 6. And then at 6 milliseconds, P1 executes, it's third, and runs for 24 milliseconds. It's over at 30 milliseconds. And so here, just like before, all three processes have finished executing at 30 milliseconds, but we just have changed the order in which they have arrived in the ready queue, but we're still using first come, first serve scheduling. Now, if we look at the wait times, P1 is going to wait 6 milliseconds because it executes after P2 and P3 have executed. Each one has a burst time of 3 milliseconds. P2 waits for 0 milliseconds. It was the first one there, didn't wait at all. And P3 waited for 3 milliseconds. So if we compute the average wait time for this order of arrival of the three processes in the ready queue, we get 6 plus for process P1, we wait time. We have 0 for P2. We have 3 for P3. We divide by 3, and we get an average wait time of 3 milliseconds. Now, if we look at this, that's a 3 millisecond average wait time, whereas before we had a 17-second millisecond average wait time. So we get much better average wait time than previously just by changing the order in which these processes, same burst time, the order in which they've arrived in the ready queue. And this illustrates this idea of the so-called convoy effect. If you have a short process that's behind a long process, that short process, because of its longer wait time, waiting for that long process to complete, that's going to end up skewing the average wait time. And so you're going to get the illusion of much poorer performance and responsiveness. And so let's consider one CPU-bound process and many IO-bound process. These IO-bound processes, because they wait, they don't spend a lot of time on the CPU executing. And so this convoy effect could mean that your IO processes are going to be slow because they have to wait for these longer CPU-bound processes to execute. So you really have to be careful about the ordering in which you present your processes on the ready queue and the selection criteria employed. And so there's another type of scheduling algorithm. One is called shortest job first scheduling, or SJF scheduling. And as the name would imply, you're going to associate each process the length of its next CPU burst. And so each process is going to be associated with a number. That number is going to be the burst time, the CPU burst time, how much time they'll spend running on the processing, on the CPU. Now, you're going to use these lengths then to schedule the process, but you're going to prefer not the first process that arrived, but the process associated with the shortest time, the shortest CPU burst time. Now, that's to address specifically this convoy effect that we talked about before. And so shortest job first is optimal. It gives you the minimum average wait time if you have a set of processes, and because it prefers the shortest burst time first in making its scheduling decisions, you're going to get small minimum or tend to get smaller average wait times. And so the practical difficulty is knowing the length of the next CPU request. You could certainly ask the user, or maybe you could compute a running total. Okay, so this is an example of shortest job first. Here we have 4 processes, process P1, P2, P3, and P4. Process P1 has a burst time of 6 milliseconds. P2 has a burst time of 8 milliseconds. P3 has a burst time of 7 milliseconds. And lastly, P4 has a burst time of 3 milliseconds. Now, by shortest job first, the first process we're going to select is the one with the smallest burst time. So that's a burst time of 3, and that's going to be process P4. So we run process P4 for its burst time, and then it exits. And then the next one is going to be the burst time of 6, so that's process P1. And then process P3 for 7 milliseconds. And then lastly, process P2 for burst time of 8 milliseconds. So here we have on the Gantt chart laid out in time, we have process P4 starts at time 0, runs for 3 milliseconds, and then it exits. Next, we have process P1. It starts at 3 after process P4 has exited, and it runs for 6. So process P1 at time 9 milliseconds, it exits. And then process P3 starts next. It's invoked by the scheduler, selected by the scheduler for execution on the CPU. It starts at time 9. It's going to run for 7 milliseconds. That's process P3's burst time. So 9 plus 7, that's 16. And at 16 milliseconds, process P3 is done. It exits. And then process P2, it runs for 8 milliseconds. It starts at 16 milliseconds time point, and it runs for 8. So process P2 starts at 16 milliseconds. It ends at 16 plus 8, which is 24. 24 milliseconds, we have all of our processes have executed. So now if we look at the average wait time, okay, well, we have a 3 millisecond wait time for process P1. So there's P1's wait time. Process P2, it has a 16 millisecond wait time. Process P3, it has a 9 millisecond wait time. And then process P4 has a 0 millisecond wait time. So we add all these up and we divide by 4 to get the average, and that's an average of 7 millisecond wait time. Okay. And so one of the practical questions then is, how do you determine the length of the next CPU burst? You can only estimate the length based on maybe some notion that the burst time isn't going to change too much based on the last measurement of burst time. So you know that when a process runs and then it leaves the CPU, you can actually measure that, and that's one of the status information points that you can get from that proc file system that I showed in Linux. So you estimate these burst times, and then you pick the process with the shortest predicted next CPU burst, because you can't know the next burst until you've actually run it. And so you take your existing burst time from the last time it was run, and then you predict from that what the next one should be, and then you make your selection criterion of shortest burst time first for the scheduler using these estimates. So you can do this by taking the length of the previous burst and use this notion of exponential averaging. So let's define a bunch of variables, and let's define T sub n as the actual length of the nth CPU burst. And so you ran it, you measured it, you have that status information for the nth burst. What you want to get next after the nth is this burst time for the n plus 1th time you're going to run it, was that next CPU burst for time step n plus 1. So that's going to be this tau. This is Greek for t. Our tau n plus 1 is going to be the predicted value for the next CPU burst. So Tn is the actual length of the nth burst, and tau n plus 1 is the predicted value. So then we set a mixture component alpha. This is our mixture component. And what this mixture component is going to do, it's going to be used to define what our next predicted burst time will be, tau n plus 1. Now, conceivably, before we had an actual burst time Tn, we also had a prediction, tau n, that we had before that we measured T sub n. And so we have this tau n from before, and then we measured Tn, and now we're going to take the previous prediction and the current measurement and use that to calculate a value of the next prediction. Okay. And we're going to use the mixture alpha to do that, where alpha is between 0 and 1 on the real number line. And so it's defined as the prediction for the next burst is equal to alpha times the current burst that was measured plus 1 minus alpha times the previous prediction. And so your predicted next burst time is going to be some amount of your current measured burst plus some amount of the previous predicted burst. And so typically alpha is set to 1/2. So your next predicted burst is going to be burst time is going to be 1/2 times the current measured burst plus 1/2 times the previous prediction. So, and you can think of it that the next prediction, tau n plus 1, is equal to the previous prediction, tau n, plus some amount, some function over the measurement at time step n. And so the next burst time, because when you run a program multiple bursts, it's not going to vary too much from one burst to the next. So this is a good estimate to make. And so there's a preempted version of this shortest job first with predicted bursts. It's called shortest remaining time first. And so if you know how much time is remaining, you take that and you preempt or halt or stop prematurely processes that are running while they're in their burst on the CPU. You stop them and switch execution to another process based on how much time remains from their burst. Okay, so let's take a look at an example, and this is of the length for prediction of the length of the next CPU burst. So here, this blue line, we have the previous prediction, tau sub I, and then Ti, that's tau, Ti, that is the measured burst. And so for each time steps here are along the horizontal axis. That's time step 0, time step 1, time step 2, and so forth. And then here we have the amount of the burst. So you have the time step, and then you have the amount of time for the burst itself. So here at time step 0, well, your measured burst is 6, and your predicted burst is 10, right? So if we do that mixture, because it's time step 0, your next prediction is 8 rather, because 6 plus 10, 50% of 6 plus 50% of 10, that's 3 plus 5, that's going to be 8, and your prediction for the next time step is 8. Okay. At time step 0, we have a predicted burst of 10, and then we measure our burst at 6. And so now when we go to compute the next burst, tau n plus 1, which is tau 1, we take 50% of 10, that's 5, plus 50% of 6, that's 3, that's going to be 8. And so the next burst time is going to be 8. That's the predicted at time step 0. So the next one predicted is going to be 8. So now we have a predicted burst, tau, of 8, and then our measured burst at time step 1 is going to be 4. So we have Tn is 4, and we have tau n is 8. So that's 50% of 8, that's 4, plus 50% of 4, that's going to be 6. So the next predicted burst time is going to be 6. And there we are, we have 6. So we keep doing that over and over and over, and we can use this weighted average, exponential weighted moving average, to calculate or predict, rather, the next burst length using the previous prediction and updating that with the measurement. Okay, so here are some examples. If alpha, our mixture, is 0, then recent history doesn't count, right? So the next prediction is going to be exactly the current prediction at time step n. So tau n plus 1 is equal to tau n. On the other extreme, if alpha, our mixture, is equal to 1, well, only the actual last burst counts. So the next predicted burst time, tau n plus 1, is going to be just that current measurement. And then if you expand this formula, playing it again and again and again, we have the next prediction is just the weighted sum alpha times the previous measurement, 1 minus alpha times the previous prediction. And if you keep unrolling this recurrence, you get an exponentiation of this mixture component, which is why it's called the exponential weighted moving average. Now, since both alpha and 1 minus alpha are less than or equal to 1, each term going back in time has less and less and less weight than its predecessor. So you kind of have a tailing off that says the further back in time an estimate was, the less that it comes into play or factors in to the next time steps estimate of the burst time. All right, so let's take a look at the shortest time remaining first scheduling criteria. And now we're going to add the concept of varying arrival times and use preemption. We're going to add that to our analysis. So let's assume we have 4 processes again, and these processes are going to arrive in the ready queue at different points in time. So you have process P1, it arrives at time 0 milliseconds. It has a burst time of 8. Process P2 arrives at time 1. It has a burst time of 4. Process P3 arrives at time 2. It has a burst time of 9. Process P4 arrives at time 3. It has a burst time of 5. And so the criteria is that when a process arrives, you look at who has the shortest remaining time, and that's the one that's going to be run, and it will preempt or halt some process that's already executing. So process P1, if we look at the Gantt chart, it arrives at time 0. There's no other process there, so it runs. It has the shortest burst time. Shortest amount of time left is 8, because it's the only one there. So after 1 millisecond, process 2 arrives. Now, when process 2 arrives, process 1 has run for 1 millisecond, so process 1 at this point has 7 milliseconds left. Now, when process P2 arrives at time 1 millisecond, process P2 has a burst time of 4. So now you have P1 in the ready queue that needs 7 milliseconds time remaining, and process P2 runs in 4 milliseconds. So which one is smaller? Well, process P2, because of the shortest remaining time. So that's going to be what's selected first. So even though process P1 is running, because at that point 1 millisecond process P2 has the shortest remaining time, process P1 is going to be taken off the CPU. The scheduler is going to choose process P2, and the dispatcher is going to switch between process P1 and process P2. So then process P1 is taken off the CPU, put back into the ready queue with 7 milliseconds left in its remaining time. Process P2 is going to start executing. So at that point, process P2 is executing, and it executes because it will execute for 4 milliseconds. And when process P2, when it's 1 millisecond into its execution time, that's at point time 2. Now, at point time 2, well, process P3 arrives in the system. But process P3, it arrives into the system at time equals 2 milliseconds, and P1 is in the ready queue with 7 milliseconds left in its execution. P2 at time 2, now at this point, it has 3 milliseconds left in its execution. Now, with 3 milliseconds left, P2, when P3 arrives, it has a burst time of 9. So P3 has a burst time of 9. At that point, P1 still has 7 milliseconds left, and P2 has 3 milliseconds. So it's still the shortest burst time. So P2 continues to execute and executes to completion to 3, 4, and 5. Now, at that point, P2 is done executing. But when we look at this, okay, at 2, P3 arrived. At 3, well, P4 arrives. Now, when P4 arrives at 3, now P2 has 2 milliseconds left to execute. Now, P4, it needs 5 milliseconds. So at that juncture, you have P1 that needs 7 milliseconds, P2, P3 that has 9 milliseconds, P2, which has 2 milliseconds remaining, and P4, which just entered, has 5 milliseconds burst time. So P2 still executes to its completion for an additional 2 milliseconds, and P2 completes. So now that P2 completes, what do we have? We have P1, which has 7 milliseconds burst time left. We have P2 has completed, so it's no longer consideration. P3 has 9 milliseconds, and P4 has 5 milliseconds. So now P4 is going to execute because 5 milliseconds has the smallest remaining time. It's 5, not the 7 and not the 9. So P4 will execute. So P4 starts executing, and it executes for the entire 5 milliseconds. Since it's the shortest one, the other two don't shrink in the amount of remaining time because they're not running. So P4 runs, and at time t equals 10, P4 is done. So at that juncture, you have P1 that has 7 milliseconds left, and you have P3 that has 9 milliseconds left. So P1 then runs for its 7 milliseconds because it has the shortest remaining time first. So it starts at time 10 when P4 is finished and stops executing because it's done at time 17. At that point, P3 runs for its 9 milliseconds and it finishes at time 26. So if we look at the average wait time, we'll do this for each one of our processes, P1, P2, P3, and P4. So in the beginning, P1, it waits for 0 time, and then it waits for time 10. So we say this time 10, we're going to subtract 1 because it didn't wait for this 1 second. So we say P1 waited for 10 minus 1 seconds. We have P2. Well, what happened? P2, it waited for 1. It arrived at 1, and it waited for 1 second, right? So it's 1 minus 1, or 0 seconds that P2 waited. Okay. P3 is P3. Well, it arrived at time 2, but it started execution at 17. So we say 17 minus 2, because that's the amount of time it really waited, because you don't wait the whole 17 when you arrive at time 2. So it's 17 minus 2 is when P is the amount of time P3 waited. So then we have P4. Now P4, it arrived at time 3, and it started at running at time 5. So we say 5 minus 3, that's for P4. We add these up, we get 26 divided by 4. That's 6.5 milliseconds is the average wait time for this shortest remaining time first. Okay. So we also have this idea of priority scheduling. And with priority scheduling, we associate a number, an integer, with each process. And the CPU then, when the scheduling decision is made, it's allocated to that process that has the smallest number, where the smallest number is associated with the highest priority. Now, there are 2 different ways of doing this priority scheduling. One is called preemptive, where a higher priority process can cause the interruption of a lower priority process. And then there's non-preemptive, where that interruption does not occur. And so shortest job first is priority scheduling, but the priority is the inverse of the predicted net CPU burst time. So that means if you have the shortest predicted CPU burst time, your priority is going to be smaller, okay, and therefore higher priority. If your predicted burst time is larger, you're going to have a lower priority. All right. But the problem with priority scheduling is this idea of starvation. If you have a priority that's always low priority, a process that's always low priority, it will never get time on the CPU and thus will never execute and never make progress to completion. And so one solution for this is something called aging. As a process continues to execute over time and makes progress, its priority is increased, so it slowly gets less and less and less high priority. And that way, those processes whose priorities were not the smallest, eventually will be the smallest, because those that had higher priority will start to increase the number in value and therefore decrease in their priority over time. And so here's an example of priority scheduling. And so let's imagine we have 5 processes, P1, P2, P3, P4, and P5, with burst times of 10 milliseconds for P1, 1 millisecond for P2, 2 milliseconds for P3, 1 millisecond for P4, 5 milliseconds for P5. Their priorities are priority 3 for P1, priority 1 for P2, priority 4 for process P3, priority 5 for P4, and priority 2 for P5. And so by priority scheduling, well, the lowest priority number or highest priority is going to be 1, right? In order of 1, 2, 3, 4, 5, and therefore process P2 is going to execute first because it has the lowest priority number or the highest priority. So we start out and we execute process P2. Now process P2, then it runs for its 1 second burst time, after P2 is done, well, the next priority process is run. That's process P5 because it has a priority of 2. So process P5 runs for 5 seconds because that's the 5 millisecond burst time. So now it started, 5 millisecond, 5 millisecond burst time. So process P5 completes at time 6 milliseconds. Now after process P5 finishes executing, the next highest priority is going to be process P1. So process P1 then runs at time 6 milliseconds, and it runs for a total burst time of 10. So this burst time of 10 proceeds from 6 milliseconds, so that is at 16 milliseconds process P1 completes executing, and now next we execute process P3 for a burst time of 2 milliseconds. So P3 starts at time 16, and it runs for 2, so 16 plus 2 is 18 milliseconds. P3 is done. So then lastly, P4 runs for 1 millisecond of burst time, so it runs from 18 milliseconds to 19 milliseconds. So if we add up all the wait times, well, we have a wait time of 0 for P2, a wait time of 1 for P5, a wait time of 6 for P1, a wait time of 16 for P3, and a wait time of 18 for P4. We add them up and divide by 5, and the average wait time is 8.2 milliseconds. All right, so with that, that's all I had. Please make sure you're keeping up with the reading, and on Thursday, I will release the take-home exam. So with that, as usual, please stay healthy, stay safe, and I will see you Thursday.